The last learning objective of this module is about distance functions and cost surfaces. So the distance function is, as we discussed previously in spatial analysis, is a function that determines distance of pixels from a source. So for example, if this is our raster image and the purple cell is our source, then the distance of the cell pink is the distance from the center of the source pixel to the center of the destination pixel. And this distance can be calculated in two ways. It could be Euclidean distance or Manhattan distance. Euclidean distance is using the Pythagoras formula and computing the distance. The Manhattan distance is not is different in a sense that it is determined along the rows and columns. So Manhattan distance between the source pixel and the pink pixel will be 4 plus 3, which is 7. And you can think of this as going through a city, and in the city you can't fly over the buildings or blocks. You have to follow streets and roads to reach a certain point. And that's why it's called Manhattan, because that's the roads in Manhattan are form a square grid, and to travel from one point to the other you have to follow the grid. But once you have the distances available, you can find a cost per unit distance, and that cost factor can be used to determine a cost surface. So a cost surface will be then the cost of getting from any pixel to the source pixel, or taking something from the source pixel to that pixel. The cost surface can be calculated using a fixed cost factor. For example, this is a source cell and the grid size is 10. So center to center distances are given in each pixel. So this pixel is 10 units away from this center. This one is 20 units away. This one is a square root of 10 plus 10, which is a square root of 100 plus 100, which is 14.1, and so on and so forth. And suppose these were the distances, and we learned that the cost per unit distance is 2. Then we can multiply this distance raster with 2 to find cost. So the cost of getting from source cells to here would be 40, 20, 44.4, 28.2, so on and so forth. So this is a local operation that we just did. We just multiplied the distance function with 2. Having said that, it may not be true that the fixed cost factor applies. The cost might be different for different cells. Let's say this could, if this was actual driving, this could be an uphill pixel, which means you will use more gas to drive through that pixel. In that case, it's called variable cost factor. And suppose this is, it's also called friction factor. Let's say this was a variable cost factor. So going through this pixel costs 3. Going through this pixel costs 3. Going through this pixel costs 1, 2, so on and so forth. So each pixel value is equal to the cost of going through that pixel. Now we can, if we were trying to get from this pixel to the source cell, then we know that half of its path is in this pixel and the other half is in this pixel. So this pixel times the cost here plus the distance here times the cost here. So 1 times 5, which is 5 units, plus 3 times 5, so 20. That's the cost of going from here to here, or from here to here. Now if we were looking at this pixel, then it has 5.6 units here and basically 5.6 units in each of these pixels. And so part of its path where it's going through this pixel is 5.6 times 2, 5.6 times 1, 5.6 times 3, and 5.6 times 1. And we add all of those values. So cost of going from here to the source cells, or from source cells to here, is 39.2. So this is how you can find the cost when the cost of traversing each pixel is variable. Now the same idea can also be applied to the Manhattan distance. So suppose we were trying to go from this pixel to the source pixel using Manhattan, this Manhattan distance or path given by these pixels, then it's half of the cell, which is 5 units in with cost 2, 5 times 2, then 5 times 1, another 5 times 1, 5 times 3, 5 times 3, and another 5 times 1. So the total cost would be 55. And you can convince yourself by testing some of these other pixels as well.